Now, many times, even sampling from the conditional distributions is not possible. And in these circumstances, we need to resort to the second main algorithm used in Bayesian computations, which is the Metropolis Hastings algorithm. Essentially, the Metropolis Hastings algorithm is used when we cannot even sample draws from these conditional posterior densities, but we can, however, sample from another distribution, say G, right? And in those cases, we are going to resort to this second main algorithm. Specifically, in a nutshell, what we do in the Metropolis Hastings algorithm is a protocol, essentially. We follow a protocol with the following steps. We start again with an initial value of the parameters, and then we sample a candidate value of the parameter from a density G, from which it's easy to sample. We then evaluate, as seen in equation 32, we compute the ratio, which is essentially a ratio of the posterior distribution of the parameter evaluated at the candidate value of the parameter and then the previous value of the parameter, multiplied by, again, a ratio of the function, the candidate, the proposal, what is called the proposal density, G, evaluated again, in this case, in the denominator at the previous value of the parameter and in the denominator, candidate value. We then sample another value, U, from a uniform distribution and ultimately compare that value of U against the ratio. And we accept that candidate or not, depending on whether the ratio is larger than the value of U or lower than the value of U. And we do this again many, many times. Right? So the idea, the key component here is this ratio, which is element in equation 32, which is the third step of the Metropolis Hastings algorithm. And this ratio has, as I said, two components. One is the ratio of the posterior distribution of the parameter, from which we cannot sample, but however, we can still evaluate it both at the candidate value, or the value of theta sampled from the proposal density, divided by the value of this posterior distribution evaluated at the previous value of the parameter. So the parameter we sampled at the previous iteration of the algorithm. So essentially, the larger this ratio of the two posterior densities or posterior distributions, the higher the likelihood that the candidate is actually a good candidate. And we correct this ratio, or we multiply this ratio by the second component, which is the ratio of the proposal density evaluated at the previous value of the parameter and at the candidate value. This is sort of an adjustment to account for the fact that some proposal densities might disproportionately choose some values of the parameter rather than others. Now the question is, well, what is a good G? What is a good proposal density? What is a good density from which we can sample candidates? And here the Bayesian literature is very extensive. However, a couple of proposal densities that have worked very well for me in applied work are random walk normal and random walk uniform proposals. Essentially, when we are working with a normal random walk proposal, what we do is we draw a candidate value for theta from a normal distribution with mean at the previous value of the parameter and with a certain variance, or we can draw the proposal density from a uniform distribution, again centered around the previous value of the parameter. Okay? And I go into this in much more detail in the slides, but the point is that by using symmetric proposals, such as a normal or a uniform, the computation of the ratio becomes simpler and essentially just reduces to a ratio of the posterior densities evaluated at the previous value of the parameter and at the candidate value. The overall point is using symmetric proposals such as a normal or as a uniform helps simplify this process. Okay? Let me give you an example of when one would use the Metropolis Hastings algorithm rather than a Gibbs sampling. And suppose, as in this exercise, we're trying to draw inferences about the correlation coefficient of a bivariate normal distribution. Right? We have a standard bivariate normal, and we want to say something to draw inferences about rho, the correlation coefficient. Right? And as usual, posterior is proportional to the likelihood times the prior, and assume that we adopt a uniform prior for rho, a uniform between -1 and 1, which is are the bounds of a correlation coefficient. Now, the posterior distribution of rho is given by this equation here, which, as you can see, very easily verify, doesn't have a closed form. We cannot really sample from this distribution. We cannot also not use the Gibbs sampler. We have only one parameter. How can we condition this into a conditional distribution? Doesn't work. So essentially what we're going to do is we're going to use a Metropolis Hastings. So again, what does it mean using a Metropolis Hastings? We need to come up with a proposal density. We need to generate candidate values from that proposal density, and then compute the ratio and compare it to the value of a variable drawn from a uniform distribution. For instance, given that rho, the correlation coefficient, is bounded between -1 and 1, a simple proposal would be a uniform proposal density with very small increments. So at each iteration of the algorithm, we start from the previous value of rho and sample a value from a uniform between -0.1 and 0.1, for instance. So as to allow the sampler to explore the whole possible space of the parameter rho, which is -1 and 1. So again, in our problem, the idea is we start with a certain value of rho, for instance, 0, right? And we start at each iteration of the algorithm, we draw a candidate value from using a uniform proposal. We evaluate the posterior distribution of rho, which we know. It's just that we cannot generate values from this, but we know that once we have a value of a rho, we can plug that value of rho here, and we can compute this value. So we evaluate this posterior distribution at the candidate value of rho and at the previous value of rho, compare it with a U drawn from a uniform distribution, and then accept this candidate value as the new value of rho or not, depending on whether the ratio is larger or smaller than U. You have an accompanying script called Metropolis Hastings algorithm for rho in R, which you can use to see how this actually works in practice, how these 5 steps actually work in practice. And once you do that, you obtain something like this. We start drawing values of rho, starting from 0, and very quickly the values of rho stabilize around -0.6, which is the true value of rho in the exercise. Now, in most cases, so this Gibbs sampling and the Metropolis Hastings algorithm are, as I mentioned, the 2 main algorithms used in modern Bayesian computation. For most or for many practical problems, we're going to use both in estimation of any model. So for instance, you have an example here in the slides and also in the scripts of a hierarchical logit model in which you have n individual observations nested within j countries. So Equation 37 gives you the equation for a hierarchical logit model with country-specific random effects drawn from a normal distribution with mean zero and some variance sigma square. And doing computations, you can see that the regression coefficients of the betas have no closed form. The random effects, also the posterior distribution, have no closed form. However, sigma square, the variance of the random coefficient, random effect, the country random effects, they do have closed forms, have an inverse gamma posterior distribution. So here, when estimating this hierarchical logit model, one would combine two steps. One would use essentially, and here are the posterior distributions for you to take a look when working through this exercise. But the point is that our Bayesian estimation approach in this setting would combine Metropolis Hastings steps to obtain values for beta and for the country-specific random effect, and a Gibbs sampler to draw samples for sigma square. And again, in many cases, or many interesting problems, you will have to combine both Metropolis Gibbs sampling and Metropolis Hastings steps. You also have another exercise to estimate a hierarchical probit rather than a logit. And you will see that in the case of the hierarchical probit, everything can be done using Gibbs sampling, because in this case, in the probit model, we can break the problem of the problem of deriving joint posterior distributions into a series of conditional posterior distributions.